So to talk about Jacobians, it's good to have a little understanding of the very basics of linear algebra. Now, I'm going to be real with you. I'm not a linear algebra. I know zero linear algebra other than this. I'm not even really a Calc 3 expert, to be honest. I've been learning Calc 3 by making these videos, and I only make a new video to this series when I fully understood the concept. So that's why the Jacobian video has been kind of delayed. But I'm not a linear algebra expert at all. I'm not even a beginner. But this is what I understand in order to help me for Calc 3. The idea of linear algebra is this idea of transformations. It's just I honestly I don't I need to learn linear algebra like what it's really about. But in linear algebra, you deal with these transformations where you're taking let's say a set of coordinates in the UV space, like some sort of plane, right? And then I guess it makes more sense to start in XY. You're taking these points in the XY plane and you're doing these transformations. Where you end up with a new set of points in the UV plane. So you're kind of transformed. So if you have a region in the XY plane, you've transformed it into something else. And you can go backwards as well. And what I have right here are the equations that kind of say, hey, X, right, to transform from UV to XY, right, to go this way, then we have to set X equal to some constant A times U plus B times V. So, for example, just to give an example, let's say we had X equals 3U minus 2V. So at, let's say this point right here was 1, 2, then if you were to do 3 times 1 minus 2 times 2, you would get -1. So my X coordinate, this point, has an X, when transformed, it would have an X coordinate of -1. To find the Y coordinate, right, let's say Y is equal to 4U plus, let's say 5V. So if I do the same thing, 4 times 1 plus 5 times 2, I would get 14. So this coordinate, when transformed, would end up at -114. So one thing you notice is that, hey, I guess maybe not you notice, I haven't made it clear, but this is a parallelogram, right? This does not have any curves. All the lines are so straight, and as you can see, these two side lengths are parallel with the v-axis, and then these two side lengths end up being parallel, not with a v-axis anymore, but just parallel with each other. And you can see the same thing for these two side lengths, which might correlate to these two side lengths right here. And this is because this is what we call a linear transformation, right? It's AU time plus BV, right? So the one way you can kind of think about it is like, oh, if I have some sort of change in U, I guess my change in X would just be proportional, right? It's just A times U. It's like this linear, there's this linearity, I guess. If you have a U squared, you can imagine that, hey, if I double U, right, then my X value is going to be like quadrupled. I don't know, right? Like, it's going to be something like that, where you're going to start getting curves when you do this transformation. We're looking at linear transformations. Now, one question I have for you is, how much times bigger? Let's say I have a rectangle, a square or rectangle right here, rectangle. And, if I were to give you this is a 5 by 4 where the lower left corner is 3, 1, right? You could figure out the area of this, it's 20. And you can, if I gave you A, B, C, and D, you could figure out all these points, right? Because you know the side lengths, you can find this point, transform it over. And you can find the area of this parallelogram. You can use a cross product. There's probably a more geometric, like pure geometry way to do it. But point is, you can find how much this area, how much more this area is equal to, or sorry, I need to shut up. I need to think before I speak. You can find how many times larger this area is compared to the original. Now, here's the thing. Because of this linearity, no matter where this rectangle is on our XY or UV space, the ratio between the XY area to the UV area is constant. And I'm going to prove that to you. And I'm going to prove, or I guess kind of derive, what the ratio actually is, like what it ends up being in terms of A, B, C, and D. So let's go ahead and let's just think about this, right? If I'm going to transform this over, we're going to have, let's say we have so we're going to have what, 0.1, 0.1, 2, 3, 4. And we could just say 1, 2, 3, 4, right? We don't necessarily know which one correlates to which, but we do know like, oh, 1 and 2 are connected, 1 and 4 are connected, that sort of thing. But it could be like 1, 2, 3, 4. I don't really know. But the point is I can find each of these points, right? So for point 1, I can find the xy coordinates using the transformation. So it would end up being A times U initial plus B times V initial for the x coordinate, and then C times U initial plus D times V initial. Now, for point 2, the point here, right, this is really U initial and then V initial plus change in V. So I would have A times U initial plus B times V initial plus change in V. And then I would see U initial plus D V initial plus change in V. And you can imagine, right, using these change in U and or delta U, delta V, I can find all the points, right? Because then point 3 is going to be A and then U initial plus change in U plus B V initial plus change in V. And then C, I want to make sure I'm not making any mistakes. And then last but certainly not least, I'm going to have point 4, where now it's going to just be, just a change in U, right? So A and then U initial plus change in U plus B V initial, comma, C U initial plus change in U plus D, or just plus DV initial. Okay. So what I'm going to do right now is I'm going to find the area of the parallelogram now, right? So this area is pretty cut and dry, or I don't know. I don't know the saying. It's going to be change in U plus change in V, right? So now for this area, what I'm going to do is I'm going to essentially create two vectors. I don't want to draw over the line, but okay, maybe not like that. But let's just draw over. It's fine. So we're going to have this vector right here and this vector right here. And I can take the cross product of, we can call this like V1. Yeah, we can call it V1. And then we can call this V2. So, and I'll use the vector notation to kind of differentiate between the V like axis or variable and versus the vectors. We can take the cross product and find the magnitude, and that gives us the area, right? Because the magnitude is always AB sine theta, or the magnitudes multiplied together times sine theta, and that's the area of a parallelogram. So let's find these vectors, right? This is just the difference in 0.4 minus the difference in 0.1. Well, what you notice is, 0.4, if I were to distribute the A U initial, I have A U initial plus A times change in U plus B times V initial. So what I'm going to have is when I distribute, I'm going to have this A U initial plus B V initial term. Right? Well, when I subtract that from the x coordinate of 0.1, right, I'm just going to be, because that's the same thing. So I'm just left with A times U initial. Does that kind of make sense? I don't want to write out all the algebra just to save some time, but hopefully you can see that when I distribute the A to each side, I'm left with A U initial plus delta, or A times delta U plus B V initial, which get canceled out when I'm trying to find the difference in x coordinate, right? Because that's how I find the vector components, right? I just look at the change in x, which is just going to equal x4 minus x1. And when I subtract those, I'm left with just A times change in U. So I know V1 is just going to equal, well, the x component is just a times change in u, right? What's going to be the y coordinate? Well, you just subtract the y coordinates like so, and you can see the same thing. I distribute the c over. I'm left with cu initial plus dv initial, which I have right here. When I subtract, I'm left with just c times change in u. And I encourage you to pause and maybe write out the algebra if you're a little lost. But the idea, hopefully you can kind of see the idea, is like these changes in v's and changes in u's kind of arise like these vectors, right? Because these vectors kind of tell us the difference. So there's kind of that connection there. So now we're going to have v2, very similar, right? This time, you just kind of have to be a little bit more careful because you can see the change in x is negative. Will that make a difference? Okay, let's just roll with this and let's just see if this works out. Yeah, I think it should be good. Okay, even though the negative, I think we ignored that. What we're gonna do is just kind of say, okay, same thing, right? AU initial, if I distribute the B, I get BV initial times, or B delta V, B delta V, and then I get D times delta. So yeah, I think in reality, I think this picture is a little bit wrong because in reality, a delta V, an increase, would lead to, yeah, so it should be flipped. I'm sorry, my picture's a little bit wrong. I think it should be 1, 2, 3, 4. But it's not a big deal. You can see this derivation is still going to work out just fine. D times delta V for the last step, right? Because when I distribute, right, D delta V, I have the up. So now what I'm going to do, I should really add the kind of tails or flares, whatever you call them, is, well, let's take the cross product. So V1 cross V2. So if I were to, this is just like kind of unit 1 or 12 or however you want to think about this. A delta U, C delta U, B delta V, D delta V, 0, 0. So you can see first things first is when I'm going to start taking this determinant to find the cross product, when I do the I component, I do C, this component times 0 minus this component times 0. That just becomes 0. Same thing for the J component, right? This component times 0 minus this component times 0, that becomes 0. And the only thing that's left with is then K, right? This component times this component minus this component times this component. So only the K component's present, which makes sense, right? K, anything in the K direction will be perpendicular to both. Otherwise, it's not going to be perpendicular if it has any components in the I or J direction. So what I'm left with is now A delta U times D delta V minus C delta U B delta V K hat, right? And this is the only direction. So this actually ends up being the magnitude. So the magnitude, which is the area, I'm going to say area, is going to equal A delta U D delta V minus B delta V C delta U. And what do you notice? Well, I'm going to have a delta U delta V component or term in each term, right? So I can factor out delta U delta V. And this, actually, I kind of spoiled it. Whatever, I'll just, you're going to kind of notice AD minus BC. So this is right here the original area, right? This is what the area initially was. And then this term right here is the factor change. So I'll say, or I don't know, factor, like times change, right? How much bigger or larger, how much by what factor did the area change? What does this kind of look like? Well, if you think about it, this ends up looking like A, B, D, C if I were to take the determinant, right? Oh, I did it backwards. This looks like the determinant because I'm doing A, B, C, D, right? So A times D minus B times C. So the factor change. So the ratio between the original area, or the area divided by the original area. So area over OG area is going to equal A, B, C, D. Now, we're going to deal with not just linear transformations. We're going to deal with all sorts of transformations for Jacobians. But you can notice that, hey, this is x as a function of two variables. This is y as a function of two variables. So what is the partial derivative of x with respect to u? It's a. And then with respect to y, it's b. I'm sorry. With respect to the partial derivative with respect to x, the partial derivative, oh my god, of x with respect to v is b. Right? So partial x, partial u, partial v, partial u, partial v. This is partial y, partial u, and then partial y, partial v. Right? Why am I worrying about partials? Well, the reason is because my transformations are not always going to be linear, but if I were to zoom in, because remember, when we're taking integrals, we're really worried about these delta, this is going to be du, dv, right? It's going to be really small changes in du, dv when I'm taking the total integral. So you can approximate at that point the transformation as linear, where the little change, like the partial derivatives end up being kind of the constants in this case. Hopefully that makes sense. This is setting us up for Jacobian. So we're going to see why on earth I'm doing all this, or why I would want to maybe do all this. All right, thank you for watching.